Assalamualaikum and selamat sejahtera. In this video, we will discuss three-phase uncontrolled rectifiers with resistive loads. Before we focus on the rectifiers, let's do some revision related to the three-phase power system. The circuit in the circle shows a Y-connected voltage sources. Based on the configuration, we can see these voltage sources are connected at the same neutral point. Because of that, they are supplying phase voltage in the system, where VR supplies voltage for the red phase, VY for the yellow phase, and VB for the blue phase. And you can write the equation for these voltages as follows. According to the voltage equations, we can say all phase voltages have same wave shape, which is sinusoidal, with the same amplitude value, and they are running at the same frequency. However, based on the angle values, we can see that all phase voltages are separated from each other by 120 degrees. Next, let's look on these voltages. According to the circuit diagram, these voltages are measured from phase to phase or line to line. Therefore, these voltages are called line voltages. And if you complete the connection between each line voltage, you can see the line voltages are connected in delta configuration. Later, in order to obtain the equation of these voltages, you need to apply KVL inside the loops. Based on the equation of the line voltages, we can see that the peak amplitude of the line voltages is higher than the peak amplitude of the phase voltages. Other than that, based on the phase angle values, we can say that the line voltages are leading the phase voltages by 30 degrees. In the three-phase system, it is crucial to know how to sketch the voltage waveforms correctly. Usually, I will sketch 6 columns of 60 degrees in width. Next, I will use the voltage equations to sketch the waveforms. From the equations, you can know the wave shape of the waveforms, the peak amplitude value, and the frequency value, and also the starting time of each waveform. Now, let's sketch the waveforms together. We will start with the red voltage. Since the phase angle of the red voltage is equal to 0, therefore, the starting time of this voltage is also at 0 point. Next, we will sketch the yellow voltage. Based on this equation, we can see that the yellow voltage is lagging the red voltage by 120 degrees. Therefore, the starting point of this voltage should be at omega t equal to 120 degrees. Lastly, we will sketch the blue voltage, and according to the equation, the starting time for this waveform should be at omega t equal to 240 degrees. Now, we have a complete voltage waveforms for the three-phase system. This figure shows the circuit topology of a three-phase uncontrolled half-wave rectifier with resistive load. As similar to the single-phase half-wave rectifier, the three-phase half-wave rectifier is capable to rectify only the positive half cycles of the three-phase voltage waveforms. Based on the number of the positive half cycles, therefore we need 3 diodes to conduct the line currents. Based on this circuit diagram, we use diode D1 to conduct the red line current, diode D2 to conduct the yellow line current, and diode D3 to conduct the blue line current. Other than that, we can see all these diodes are connected to a Y-connected voltage sources. Now, I will explain the operation and how to sketch voltage and current waveforms of the half-wave rectifier. Principally, only one diode will turn on at one time. To know the switching sequence of these diodes, we will refer to the potential value of the anode terminal of these diodes. For your information, the potential value of the anode terminals is directly proportional to the amplitude value of the phase voltages. Typically, the diode with the highest potential of the anode terminal will start the current conduction. Before we analyze the waveforms, I will remove the negative half cycles to make our analysis easier. Now, let's start at omega t equal to 0. At this angle, we can see the amplitude of the blue voltage is higher than the red voltage. Therefore, diode D3 will turn on. This diode will conduct the blue line current until this intersection point. At this point, the diode will stop the current conduction because the amplitude of the blue voltage is equal to the red voltage. And when you analyze the circuit, you can see that the blue line current is also the output current of the rectifier. And the wave shape of this output current is following the wave shape of the output voltage waveform with a smaller amplitude value. And when you refer to the second equation, you can see that the output voltage waveform is following the wave shape of the blue voltage waveform. Based on these equations, you can sketch the blue current waveform, the output current waveform, and the output voltage waveform as follows. Next, we will focus on this intersection point. After this point, we can see the amplitude of the red voltage increases and higher than the blue voltage. Therefore, diode D1 will turn on. And this diode will conduct the red line current until the next intersection point. By analyzing the equivalent circuit, we can see from the first equation that the red line current is also the output current of the rectifier. And the wave shape of the output current is following the output voltage waveform with a smaller amplitude value. And based on the second equation, the wave shape of the output voltage waveform is also following the wave shape of the red voltage waveform. Therefore, we can sketch the red current, output current, and the output voltage waveforms as follows. Subsequently, after the second intersection point, we can see the yellow voltage has the highest amplitude value. Therefore, diode D2 will turn on until the next intersection point. After the last intersection point, we can see that the blue voltage has the highest amplitude value. Therefore, diode D3 will turn on once again. Based on these conduction ranges and the previous circuit analysis, therefore, we can sketch the line currents, output current, and output voltage waveforms as follows. Now, give your attention to the wave shape of the output voltage waveform. Based on the graph, we can see that the output voltage waveform consists of 3 voltage pulses. Because of that, the half-wave rectifier is also known as a 3-pulse rectifier. Next, please focus on these conduction ranges. From these levels, we can see that the output current of the rectifier commutes from one diode to another diode at every intersection point. Therefore, these red vertical lines are referring to the commutation lines of the half-wave rectifier. Other than that, based on the ranges, we can calculate the conduction angle of each diode. Based on the labels, the conduction angle of each diode is 120 degrees or equivalent to 1/3 of a complete cycle of the half-wave rectifier operation. I will end this video by calculating the ripple factor of the output voltage waveform. Based on the equation, we need to calculate the average output voltage of the rectifier. However, based on our previous discussion, we know that the output voltage waveform is generated from 3 voltage sources. Because of that, each voltage pulse has a different equation. To simplify the analysis, we must refer to the rate voltage as our reference. By referring to the output voltage waveform within this range, therefore, the t value is equal to 120 degrees and the range of the integral function is in between 30 degrees to 150 degrees. Make sure you convert all these angle values into radian values. Eventually, the average output voltage of the half-wave rectifier can be represented as follows. Eventually, the average output voltage of the half-wave rectifier can be represented using this equation. Next, we can calculate the RMS output voltage using these following equations. After you watch this video, make sure you complete the derivation of both voltages. Therefore, you can verify these final equations. Next, if we consider the peak amplitude of the line voltage equals to 1 volt, therefore, the ripple factor of the half-wave rectifier is equal to 18.3%. Furthermore, if you calculate the rectification ratio, you can see the rectification ratio or the efficiency of the rectifier is equal to 96.8%. Lastly, since each diode can conduct current for 1/3 of a complete cycle of the rectifier operation, therefore, you can calculate the average and RMS diode currents using this equation. That's all from me. We will continue our discussion in the next video.